Hello everyone and welcome to the 11th lecture of the course Advanced Structural Analysis. We have briefly covered the introduction to the force method with an overview of the flexibility analysis of the given system. With this week we will start with the displacement approach and we will try to see it from the perspective of the simple stiffness method. These are the brief content. We introduce the displacement method in this, we define the definition of the stiffness coefficients, and then we look at the steps of the analysis. The typical methods, as we see, the displacement method is very much similar to the force method in terms of certain of its attributes, and while looking at the method we will try to recall that what we did in the force method so that we can draw the parallels between both the methods. As a method primarily looks to evaluate the unknown joint displacements, we call the method as a the displacement method. When we say the displacement, we have already said that includes both the translations and the rotations in the given system. We evaluate the systems of the displacements by considering an initial system which is a kinematically determinate system. This is different than considering the statically determinate system which we do in the force method. Then we evaluate the amount of the forces in the direction of each of these degrees of freedom, and we write the equilibrium of these forces in the subsequent systems, and the equilibrium of these forces typically is the primary condition which we define to evaluate these unknown displacements, and that is what we also call this as the equilibrium method for the given system. And while defining these unit deformations in the given system, we try to generate the internal forces which are identified in the given system, and this gives us the definitions of the stiffness in the given system, and that is what also describes the method as a simple stiffness method. So what we realize that the standard force method, we have the unknowns which were the reactions, whereas the displacement method entertains primary unknowns as the unknown displacements of the given system. The force method converts the initial system into a statically determinate system by releasing the unknown redundants, whereas the displacement method considers the initial system as a kinematically determinate system by restraining all the degrees of freedom of the given system. We get the conditions of the compatibility to know all the unknown parameters of the redundants in the force method, whereas we utilize the equilibrium conditions in the direction of the given release reactions or the release deformations of the system to calculate the unknown displacements. Now, the flexibility approach or the flexibility is typically defined as a parameter to evaluate the system response when it comes to the force method, in which we apply the unit load and calculate the deformations in the given system, and then by taking the summation of those deformations we define a consistent deformation for the given system which satisfies the compatibility condition. Whereas when it comes to the displacement method, we identify the system to be undergoing with a unit displacement, and corresponding to that we define the internal forces appearing in the members, and by taking the subsequent summation of all those member forces we define the net equilibrium equations of the given system. So in this manner we identify a unit load kind of approach when it comes to the force method, and we come up with a unit displacement kind of an approach when it comes to the displacement method. Now, before going into the formals of the basic displacement method, we understand few points, which is, as we said, that this is a problem which we want to initially solve, as this problem was also our consideration in the force method. As a starting case, we try to consider that all the degrees of freedom which are available in this problem to be identified. So we know that with respect to the given problem, if we consider that the system is having axial deformation not possible, we can have only rotations at each of the joints which is the unknown set of displacements available. So we have n number of joints, at each of the n joint we have one unknown rotation. As a first step, we convert our system into a kinematically determinate system. We have discussed earlier that a simple system of a fixed ended part is a kinematically determinate system, which means that a system which is having two ends fixed will always be considered as a kinematically determinate, because we know all the displacement conditions at the two ends of the given system. So now when the question comes up to define the kinematically determinate system for this original problem, we have a unique choice because we restrain all the rotations of the given system which are available or which are free to take place, and while doing so we will generate a system which is a system having all the joints fixed in the given problem. Now, irrespective of a problem, irrespective of the loading, irrespective of the support condition, as many times we try to solve this given problem, we will try to come up with only this given condition of the static kinematically determinate problem. If any of the user want to define the given system to be converted into a kinematically determinate system, this is the only one unique choice defined for the given problem, and this is also one of the basic difference between the force method and the displacement method. The second criteria, as we understand, any of the loads which are active on the given system, and a system which is a fixed ended system, will typically have the effect only within the span of the given system, which means that if I come up with a member having, say, a system like this, as a condition that we have some loading provided on the multiple supports, and now as a first step I consider my system to be kinematically determinate by restraining all the degrees of freedom, the effect of the load which is active on the span, if I define it by the names, say AB and BC, the span AB will only entertain the load which is active on the span AB of the given system, whereas the span BC will only entertain the load which is active on the span BC of the given system. This is as simple as saying that if I have a load active on this span and the members are restrained fully for any kind of a translations and rotations, I can break the system into two parts as well, having both of their supports intact and completely fixed and the subjected to the loads as defined originally on their span. So, any of the load which is appearing on the span BC is only going to affect the support reactions on the joint B and C. Any of the member load which is active on the span AB is only going to affect the support ends at A and B of the given problem. That means the joint B will have some common reactions appearing from both the sides, but as long as if we go with now a multiple support system where we have restrained the given system and we have considered a load which is active over here, the influence of this load will only be felt into the span on which it is active. Any of the other spans will be completely free from the load which is active on this given span, and this is one of the main classifying criteria where we can describe the support reactions for these fixed ended systems very easily. As the next part of the system, as we start to release the given reactions of the given system, we also recall that we have already given that corresponding to the amount of rotations taking place in the given system, the fixed ended reactions and the corresponding translational reactions are also notified. In the similar manner, if the system undergoes some kind of a translation delta, the fixed ended moment reactions and the vertical shear reactions are also calculated and they are known to the user. In most of the situations, many times people have the doubt with respect to their directions. So, what one can easily do, as a given system is trying to undergo deformations like this, we can try to define that this is the possibility of the rotation which the system want to take up. So, the reaction which will be generated will be opposite to it. At the same time, the system which is going to consider over here, we have to have the reaction corresponding to this given axial line. This is the kind of deformed shape which the system is taking place. This is the possible rotation in which the system wants to move. To resist it, the reaction has to be opposite. So, this can be easily verified that these values which have been identified, even if you do not remember their directions, you can easily do it by the simple deflected shape of the given profiles. Now, using this idea, we will try to go forward with the multiple problems, and what we have summarized over here, that a kinematically determinate system is a unique system for a given problem. Any of the load which is active on the given system can only have the influence on the given span on which it is active in a kinematically determinate system. Any of the load which will appear at the joints of the given problem will not influence any of the support or any of the members of the given system other than the support at which it is active. So, if I say that I provide one vertical load at this given support, so this load will only get reaction directly at this point. It is not going to provide any deformation to this member or the another member or other supports of the given system. So, this is a very simple idea where we consider that a fixed support is a fully rigid system. So, any of the load which is active on that will be getting reactions there itself. It will not translate to any other point of the given member. At the same time, we also now recall that for all these standard cases on a given member, as we are considering that fixed ended members subjected to some load can have the influence of the end reactions only on the given span. So, that is why we now go back to some of the standard results which we evaluate in the force method for the standard fixed ended reactions of the kinematically indeterminate systems and take the help of those to analyze the systems using the displacement method. So, when it comes to the say solution of a method like evaluating the system reactions corresponding to this distributed load, we take the help of the standard force method solutions, and from there we try to evaluate what will be the values of these two end moment reactions, what will be the values of these two support reactions of the given system. We can do this for multiple cases of the loading as described here. Now, as a basic of this displacement method, we will now try to define the basic approach. We consider that the initial system which is defined to us is a kinematically indeterminate, because we have number of degrees of freedom which are available, which are all the rotations described at multiple supports of the given system. As a first step, we convert our system into a kinematically determinate system. So, we restrain all the degrees of freedom and then we restrain the system such that it is a fixed member for the given problem. This system is subjected to the external load. Corresponding to the given external load, we calculate the reactions at the ends of the given problem. Now, as we have already discussed, this part of the reaction calculation is much more easier. One can simply consider it as a example case, like if I have this as a original problem and this member is subjected to these two kind of a loading, as a first step I will convert my system into the fully constrained system like this, subjected to this reaction and this load over the given system. Now, the reaction which will appear in this system will be only due to this span load of the given member. So, if this is the load P, I can describe that this value will be P by 2. The moment over here will be PL upon 8 as per the given calculation. The reaction over here will be P by 2 again for the given system. Now, at the span BC of the given system or the second span of the given system, I will again calculate the reaction. So, this support is a common one. So, it will get the reaction which is say WL by 2. Over here also the reaction will come WL by 2, and over here I will get the moment WL square upon 12, and at the center point I will get the net moment which is WL square upon 12 because of the span 2, and because of the first span I have a moment which is in the opposite direction, and that can be represented as PL upon 8 in the given problem. So, with this idea in mind, I can understand that evaluating these system reactions for a fixed ended system is much more easier, and for our help we already have a system of these cases which are available to us. From these standard cases we can easily evaluate the system reactions for the fixed ended part. Now, as we do the process, we have calculated that the first system, which is the kinematically determinate system, and it has got all the reactions of the given system. As a next step, we understand that the given system of a kinematically determinate part is not same as the original system. So, what we do, we consider the given problem with respect to the first case of the deformation which is available over here. If I say that this amount of the deformation is theta 1 in the given node, we provide the unit amount of theta 1 in this given condition. With respect to the unit theta 1, the system will undergo some kind of a deformation profile like this, and once the system undergoes deformation, we will have the set of reactions or the forces which will be generated in the given problem. Once we are able to know these set of forces in the given system, we can calculate their values, and these are the corresponding values due to the unit rotation provided in the direction of theta 1. Further, I can add one more system on top of it. I can bring the second rotation of the given system, which is theta 2 in the given problem. So, our intention is that initially we considered this problem which is to be solved. We restrained all the degrees of freedom, so that now the system is fully restrained but kinematically determinate. In this problem, as we want to reach to the original problem, one by one we release all the degrees of freedom. First we release theta 1, then we release theta 2, and for each of the cases, as we are releasing the degrees of freedom, we are realizing that the system is undergoing the deformed shapes, which will also be resulting into the reaction forces at the ends of the given system. These forces can be calculated easily based upon the expressions which we have calculated earlier for any of the rotation or the settlement of the given system. Now, similarly, we do this process for all the n number of rotations which are available in the given system, and once we complete this process, we understand that these all systems, the n number of systems with respect to the corresponding rotations being released and the system which is kinematically determinate, are equivalent to the original problem, at least in a kinematic manner. So, we say that these systems are kinematically similar to the original problem which is defined to us. When we say kinematically similar, we can now recall from the discussions of the force method, it simply means that when we look at the support A of the given original system, we understand that this is fixed. When we look at the support A with all these systems together, we realize that the condition of the system is remained fixed all throughout. That is why the summation of all these systems together will give me the same condition which is in the original problem. When I go to the joint 2, I realize that all the systems are restrained in the given joint which is corresponding to say joint 1 over here. With all these systems, the condition of the restrainment is followed except for one of the system where the theta 1 is rotated or theta 1 is provided to the given system. And if I consider that instead of theta 1 it is say the value of theta 1 only, the original displacement or the rotation of the given system, this system becomes same as the original system which has been considered in the given problem. In the subsequent manner, I can go to the summation of all these systems together and I can calculate that while all the systems are having restrained degrees of freedom, only one system which is with respect to theta 2 is being released, and that is what is the same as the original condition of the rotation in the original problem. So, what we have got that all these systems together are kinematically similar to the original problem, but we have not verified in this case whether the conditions of the forces which are net available at this given joint or in the direction of the given rotations of the given problem, are they also being followed with respect to the original problem, and that gives us the conditions of the static equilibrium, and we make these systems statically similar. So, kinematically the systems are similar, but statically the systems are not similar. So, in order to make them similar, we satisfy the conditions of the equilibrium in the direction of all of the redundants, and that gives us the extra conditions of the equilibrium in the given system. So, we write these conditions in a simple manner and then we try to evaluate them further. As a simple steps in the given analysis we understand, we will just say that these are the steps in the displacement method. So, as a simple steps in the displacement method, we first define the kinematic indeterminacy of the given system, then we define all the active loads which are active in the given system in the direction of the available degrees of freedom. This is one step which we typically do, which is identified such that the active loads of the given system are considered. Then as a third case, we convert the given original problem into a kinematically determinate system by restraining all the degrees of freedom, and then the degrees of freedom which we define for the given system corresponding to the restrained degrees of freedom, we calculate the amount of the reactions in those directions due to these active direct loads of the given problem. As a next step, we consider that we release each of these degrees of freedom which are available in the original problem, we release them one by one in the kinematically determinate system, and while releasing it, we calculate the forces in the direction of all these degrees of freedom in these release systems. And by writing now the equilibrium of the given system, we identify the necessary conditions which become the necessary conditions to solve the unknown set of displacements of the given problem. By solving these all simultaneous equations together, we calculate the unknown displacements of the given problem. As a simple step further, we now try to see the implementation of the given approach. We have considered a system which is subjected to some load. As a first step, we considered the system as restrained with all the degrees of freedom considered with respect to the external load, and we evaluated all the system reactions in the given supports. As a next part, we released the first degree of freedom in the given system. With respect to the unit value of the given theta 1, we were able to calculate the end forces or the end forces of the given system, which are typically utilized based upon these principles, that if a theta rotation is allowed, the near end gets the moment reaction of 4 EI theta upon L, the far end gets the moment reaction of 2 EI theta upon L, the reactions in the shear direction come out as 6 EI theta upon L square at the two ends. Similarly, with respect to the translation relative to the joint A and joint B, we can describe these end moments as well as the reactions of the given system. Corresponding to the axial deformation, if any of the member is actually undergoing some deformation, we calculate the axial force which is AE upon L into delta for the given system. Similarly, we can also have the condition with respect to the twisting taking place in the given system. If there is a twist amount which is provided in the given system, corresponding to that we get the twisting moment which is equal to Gj upon L into phi. Now, with these all points in mind, we can try to evaluate these end forces of the given system. We call that corresponding to each individual released reaction of the released displacement of the given system. We calculate the end forces, and now by writing the cumulative summation of all these forces in the direction of the defined degrees of freedom, we are able to write the equilibrium equations of the given system. So, as equilibrium equations, if I typically define, as a first case we have the equilibrium equation with respect to the joint or the displacement at the node 1, which is the theta 1 over here. That equilibrium condition can be described with respect to the load 1. As we have already said that the general representation of the load can be described as the regular force, or it could also be describing the moment of the given system. In cases where we are defining the degrees of freedom as the translations, it becomes force. In cases where we are defining the degrees of freedom as the rotations, it becomes the moment. So, in this particular case, these will all be the conditions of the moment in the given problem. So, we define the moment at the point 1 is equal to moment at the point 1 due to the external load system, this given moment which is applied in the given or which is generated in the given system. Then moment at this given point due to the external rotation of the given system theta 1. Then again the moment at this point 1 due to the theta 2 component, again the moment at this point due to the theta n component in the given system. And if we add all of them together, we get the equilibrium equation of the moment corresponding to this given system. I can keep on doing this for all the cases, and these are the n number of equilibrium equations which we can define for the given system. As we have already seen earlier, corresponding to each of these loads which we are describing in the given, each of these forces which we are describing, we first consider a unit amount of the displacement or rotation to take place in the given system, and with respect to this unit amount of value of the displacement, we define this condition as the stiffness of the given problem. So, we have defined this condition, say with respect to P, the force in the direction of the degree of freedom 1, with respect to the unit displacement in the direction of degree of freedom 1, and we call it as S of 1 1. Similarly, this is the force in the direction of degree of freedom 1 with respect to the unit displacement in the direction of degree of freedom 2, and we call it as S of 1 2 in the given system. Subsequently, we can define S of ij as a simple amount of the force in the direction of the degree of freedom I with respect to a unit force, unit displacement in the direction of degree of freedom j of the given system. By writing all these systems together, we simply define this condition, and this could be represented as a simplified case like this. Having these all systems together, we can now evaluate them, and we can try to calculate the conditions of the net unknown displacements of the given system. A standard way to solve these system of equations can be defined where we arrange them in the form of the standard vector and the matrix representations. We can describe these all the conditions of the equilibrium on one side, the corresponding conditions of the load due to the loading can be described on the other side, and then we can assemble all the stiffness coefficients of the given system starting with S of 1 1, S of 1 2 up to S of 1 n in the given system. Similarly, for all the system S of n 1 to S of n n in the given process, and this should be multiplied with the corresponding values of the unknown displacements which we want to evaluate in the given problem. So, as we are able to identify a standard way to evaluate these stiffness coefficients, the values of the system reactions due to the fixed ended system, and the conditions of the equilibrium are known to us, we can easily evaluate the unknown values of the displacements of the given system. So, with this we have defined a very simple procedure to evaluate the unknown set of displacement in the basic displacement method. We have not seen the evaluation of these coefficients as of now, but through a very simple method we can understand now that the displacement method, having a very unique system of the kinematically determinate system, could be utilized for the analysis of the indeterminate system in a much more effective manner, and this we will try to see through the next successive sessions. With this we stop over here. Thank you everyone.